So now we have the last speaker. We can simply ask him to try his shot on analytics. Stefan Wulfingoff, please.
Yeah, thank you. And first of all, thank you for giving me the opportunity to be here and present the work, which I like very much. It's a lot of things which you already saw in the presentation of Samuel Forest. In fact, this work has been done in cooperation with him in Évry, close to Paris, at the Centre des Matériaux. And it's exactly the same topic. And the principal aim of the talk is the investigation of constitutive equations or constitutive models, which seem to be quite promising within the framework of gradient plasticity. Specifically, I will talk on the inspection of two potentials, which are quite promising: the logarithmic potential and the rank 1 potential for the generalized stresses which arise in these theories. And we investigate these potentials by considering a special analytical and also numerical solution for a one-dimensional problem, because in one dimension very often things are more easy to understand, and if we want to investigate these constitutive models, this seems to be quite promising. Of course, there's a lot of literature on the topic, starting from general dislocation theory and kinematics and crystallographic aspects of geometrically necessary dislocations, which are heavily exploited in gradient plasticity theories. And of particular interest for the talk today is here the numerical treatment of non-smooth defect energies, and also the micromorphic approach as proposed by Forest in 2009. We will start by introducing the general gradient crystal plasticity framework, as already discussed by Samuel Forest, in order to then use this framework to investigate solutions for a laminate problem, which we then exploit to investigate these two constitutive approaches in form of a rank 1 energy and a logarithmic energy. And finally, if there is some time, I will also speak on the numerical handling, but maybe we skip this in order to get quickly to the lunch. Okay, so the crystal plasticity framework here is a gradient-enhanced framework as used, for example, by Gertin and Needleman in a very similar form, and Cordero et al. In 2010. It is based on more or less standard kinematic ingredients. First, the additive decomposition of the displacement gradient into elastic and plastic parts. So we have in a small strain framework here, and in analogy, the additive decomposition of the strain. And the plastic distortion takes the typical crystal plasticity form. And what do we want to do with this framework? We want to describe crystals. And originally, this type of kinematic framework has been proposed for macroscopic crystals, so like specimens which you could put in your machine and do tensile tests on that. And it came out that these kinematics can quite well describe the mechanical behavior, or they are a good starting point in order to describe the mechanical behavior of macroscopic single crystals. However, it was then realized after some time that, like every model, this model has some limits, which appear here when you go down with your specimen to the micro world. Like if you take, for example, a specimen which is only some micrometers large, then it turned out that using the classical theory based on these kinematics underestimates the strength of the material. So there's a certain size effect which clearly cannot be taken into account by taking only these classical kinematics, since these do not contain an internal length scale, that they are clearly not able to reproduce a size effect. Therefore, we consider here, let's say, extended or improved version of the theory, at least we try to improve it, by taking additional microscopic information into account. And this microscopic information is given in terms of the dislocation density tensor, since this is physically an object really which has a physical interpretation, because it represents an effective Burgers vector density of your underlying dislocation density. Of course, you don't resolve the individual dislocation, but you have a kind of effective description of your dislocation network. So you just put in more information and hope that the model gives a better response. And since you want to have a model which now gives a different mechanical or an improved mechanical response, you also need to say how the forces which enter the model are affected here, and therefore additional stresses are introduced, as has already been discussed by Samuel Forrest. So considering here the principle of virtual power, we have an extended set of stress powers. Besides the classical stress or virtual stress power, there are also stress power contributions as given here, where the generalized stresses M and S conjugate to HP and alpha have been introduced. And well, after some time you realize that this is not enough also for the virtual external power. You need to add a generalized term taking into account so-called, let's call it microtractions conjugate to HP at least the Neumann part of the boundary. Then you can postulate the principle of virtual power as a weak statement of your field equations and Neumann type boundary conditions. So by some rearrangements you find these, the linear momentum balance and an additional partial differential equation called here microforce balance, and in addition to the classical traction boundary conditions you also get microtraction boundary conditions. Okay, in the next step you also have to say how can I compute these stresses, and therefore you need constitutive assumptions, and this is what this talk is all about. We want to investigate promising constitutive candidates for which act as potentials for the stresses, and therefore the classical energy which is given here is extended by a defect energy. And this defect energy depends on the dislocation density tensor, and in this talk we want to investigate the aforementioned two promising candidates. The first one is the rank 1 energy, which has, for example, been used already in 1999 by Ortiz and Repetto. And the second one is the logarithmic energy, which has recently been proposed by Forrest and Guénichot in 2013. Well, if you want to motivate these energies, the first one can maybe easily be motivated by assuming that all elastic dislocation interactions are already somehow accounted for in the classical term here, and you only have to account for the dislocation self-energy or self-interaction. Therefore, there's simply a proportionality between the energy and the dislocation density. And the second one can be motivated from the backstress, which arises from the application of this energy. I will come back to this in a few slides later. Then, as I already said, these energies act as potentials for the stresses, like for the Cauchy stress and also for the generalized stress M. But here we get a problem, since this energy here is not smooth. It's not differentiable at alpha equal to 0 if you apply the rank or 1 energy, for example. So therefore we said, okay, let's see how we can describe this, and therefore we propose to treat this by using the framework given by subdifferentials. And this means that at alpha equal to 0, where the rank 1 energy, for example, is non-smooth, you cannot uniquely determine the generalized stress M, which is applied at a material point, but you can only determine an admissible range for this generalized stress M. Very similar to plasticity. And for the special case of a rank 1 potential, this admissible range at alpha equal to 0 takes a very nice form, because we can characterize this range by a, let's say, generalized yield function given here, phi g1. And the interpretation is as follows. If you apply the generalized stress M at a material point, alpha will stay 0 until M gets sufficiently large. So only if the absolute value of M takes the critical value CGB, then alpha can take values which are not equal to 0. So a little bit like a yield criterion. Therefore I call it a generalized yield criterion. Okay, now in the next step we want to investigate the behavior of these two promising stress potentials within an example. The example is given by a single slip problem, specifically the shearing of such a periodic laminate material, as shown here. The material is assumed to be composed of a soft elastoplastic phase here, given by S, and a hard elastic phase. And the slip system is assumed to be aligned with a given coordinate system. Then the only stress component which does not vanish is the shear stress component, which can easily be shown by the linear momentum balance to be constant everywhere. So it's a very simple situation here. And it is also equal to the resolved shear stress in the slip system. Also, the dislocation density tensor turns out to have only one non-vanishing component, which can be interpreted as a geometrically necessary edge dislocation density, rho h here, which can be computed from the gradient of the plastic slip. And in addition, also the generalized stress M has only one non-vanishing component, therefore we denote it by a scalar M here. The microforce balance turns out to reduce to a simple scalar differential equation, and from evaluating the dissipation we find that the plastic driving force here is simply the sum of the 1-2 components of the Cauchy stress plus the generalized stress M, which is conjugate to HP. Okay, motivated by this finding, we assume that the yield criterion is given in terms of this effective stress here. And in addition, we introduce a critical resolved shear stress as a constant material parameter and consider a rate-independent case. Okay, now this is the setup of the problem. Let's now consider how these two energies behave within this problem. Therefore, we compute an analytical solution. So only very quickly, how can we do this for the rank 1 potential given here? We start by evaluating the generalized stress M simply as the derivative of the defect energy, and we find that if the G&D density is not equal to 0, then the absolute value of the generalized stress is given by a constant CGB, and only the sign is determined by the edge dislocation density. Whereas if the G&D density is 0, then M is less or equal to CGB. Then we consider a fully plastic situation. So in the soft phase, the yield criterion is fulfilled everywhere. And in this case, the microforce balance reduces to a very simple linear differential equation here with the constant right-hand side. So very easy to solve. And we find that M, the generalized stress, is simply linear in space. Therefore, if it's linear in space, it's clearly not constant. So we find that we're not in this line here, but we're in this line here, which means that the dislocation density must vanish. So that's the result. And if the dislocation density vanishes, then also the gradient of the plastic slip, of course, must vanish, which means that the plastic slip in the soft phase is simply constant. And this makes the whole computation then very easy. You can, for example, evaluate the energy balance for such a volume, which turned out to really yield a simple analytical solution for the stress sigma 1, 2. And let's have a look at this analytical solution. It shows that this is the macroscopic stress strain curve. And it shows that the overall yield stress of the laminate composite is not only dependent on the local critical resolved shear stress, but also on this delta, which scales like 1 over S. And S is here the width of the soft phase in the laminate material. So really, a little bit like the whole patch effect, the smaller the microstructure of the material, the larger the effective, let's say, yield stress of the composite. And interestingly, it turns out that for typical material parameters for aluminum here, and this prefactor C equal to 1, the size effect becomes important when the soft phase has a size of approximately 10 microns. And this is also, interestingly, the size where in experiments the size effects become important. And in addition, as I said, the slip is constant in the bulk, therefore the G and D pile-ups are not really pile-ups, but they form walls. So you get singularities at the interface between the soft phase and the hard phase. Okay, so this was the rank 1 energy. Now let's turn to the logarithmic energy in the 1D case given by this expression here. Then you can compute the generalized stress simply by derivation. And now the whole thing gets interesting if you look at the yield condition F, which is again assumed to be fulfilled everywhere in the soft phase. So this is equal to 0. Now look at the plastic driving force. Plastic driving force is given by the resolved shear stress plus a back stress. And maybe some of you know the work of Groma et al. From 2003. What they did is they started from discrete dislocations and the elastic fields of discrete dislocations, and let's say in a statistical way derived a statistical dislocation density field theory, and they found an expression for the back stress. And to my knowledge, this is one of the most accepted, maybe even the most accepted form for back stress in this whole gradient plasticity business. And the form of the back stress is very close to the form here. The only difference is that in Groma's back stress, here this expression is not the G&D density, but the total dislocation density. That's the only difference, and this is the principal motivation of this logarithmic energy. It's this back stress here. So you can say that if the G&D density is dominant, so that your statistically stored dislocation density is small, then this is a really reasonable approximation of Groma's theory. However, if the SSDs dominate, then this is not a good approximation of Groma's theory. So, but if the G&D density is really large, then everything's fine. And yeah. Okay, so now in the following slides, let's assume that the G&D density is really dominant, so we have a good approximation. And consider the microforce balance again, which gives us a differential equation, which we can solve analytically. And well, it's a bit complicated expression, so let's just have a look at the curves first. Yeah, and if we consider the behavior, this is again the laminate behavior for different sizes of the soft phase, and we find that again we have a size effect, and with decreasing size, mainly the yield stress increases, but there's also a small effect on the hardening, and the dislocation pileups are given here in terms of the dislocation density. They take a more or less typical form, I would say, for gradient plasticity simulation. Now, what I did not yet say is that the logarithmic energy is a bit problematic. You can see this if you plot it. So this is the energy in terms of the G and D density, and you say that in the region of small G and D densities, we find that the energy is neither smooth nor convex. So really a bit problematic, and this is, well, you can interpret it like this. We said that for small G and D densities, the energy approach is not reasonable because then the SSDs dominate, and well, we don't have a good approximation of Gromer's theory. Therefore, we said, okay, let's regularize the energy, for example, by simply putting a quadratic energy here. Then we get for special choice of the parameters of this quadratic energy, we get a C2 continuous regularization of WG. And interestingly, there's only one free parameter for your energy, and that's this point alpha 0. Everything else is fixed, so you have a Burgers vector and elastic moduli in there, but that's really the only free parameter of your energy, and this parameter needs a certain interpretation. And interestingly, if you assume that alpha 0, or if you interpret alpha 0 as a characteristic value of your statistically stored dislocation density, then you get a really nice interpretation. So let's have a look. If you take then this regularized energy, the back stress is given here. Now, if the G and D density is larger than the characteristic SSD density, then we are here, and you get the back stress which I just showed here. However, in this region, if the G and D density is less than the characteristic SSD density, we take this back stress and look at the SSD density, which appears here. Suddenly, you don't have the G and D density in the denominator, but the SSD density, which means that now, in this case, your characteristic SSD density delivers the characteristic length scale of your backstress. And this is a very interesting result because we just introduced the blue curve for regularization reasons, but we also find a very nice physical interpretation for this regularization. Okay. Now, as I said, there's only one free parameter of your energy, that's the SSD density, which you have to guess. And this is usually a bit complicated because one is maybe lucky or you might be lucky if you have a rough idea of the order of magnitude of your SSD density. And therefore, we looked at how sensitive the results are on your guess of the SSD density. And the result is shown here. So you have, again, the same results. And we varied this free parameter within 3 orders of magnitude. So really rough, if you really have a rough idea of your SSD density, you might only guess the order of magnitude correctly. Well, and we find that the results change. There is a dependence, but it's not too strong. So the curves, well, let's say they're not too far away from each other, which means that this result shows that if you have a rough idea of your SSD density, you may hope that you already get reasonable results for your size effect without explicitly computing the total dislocation density or whatever. Okay, so this really gives you an interesting gradient crystal plasticity approximation of the statistical theory of Gromer et al. From 2003. Okay, we already saw these curves. So this is the cyclic loading curve, and some of the rest already discussed that this is also observed in experiments, so also quite interesting result. And in order to compare these two energies, let's have a look at the scaling behavior. You see here the yield stress as a function of the size, and the scaling behavior is very similar in this application. Both scale roughly like 1 over S. Okay. And yeah, there's a lot of numerical stuff also, but I think I will skip most of it and only let me just quickly say that in order to solve, for example, this problem was solved or obtained numerically, and we did this with the Lagrange multiplier approach here. And let me just say that this gives a really interesting solution scheme. Because in your finite element model you usually use a subroutine at your integration point, and in fact here we do not get only one but two user subroutines, and the second one is very interesting. I talked about this yield criterion or generalized yield criterion function phi, and this yields also a local algorithm which is very close to classical plasticity algorithms. Now look at the computation of your generalized stresses. We start with the trial step, compute trial generalized stresses and a trial value for your generalized yield criterion. If the yield criterion is not fulfilled, then the trial step was right. Okay, then you have your stresses here. Else, the density tensor alpha will not be 0, but take a certain value, which we can compute by evaluating the direction of the generalized trial stress here. And also the stress is computed by taking the trial stress and projecting it back onto the generalized yield surface. And I think this is interesting because it shows that, and also the computations show that you get an algorithm which we all know is quite well suited for applications. It's quite robust and efficient, and this can then also be used for rank 1 or generalized non-smooth defect energies. Okay, so maybe I skip the summary in order to allow you to, and also me to get to the lunch. So thank you for your attention.
Potential. In the first case, what you call rank 1, which I find misfortunate because it has nothing to do with rank 1, it's a linear close energy, and compared to that you have a logarithmic type energy which is a little bit larger. And the point is that the basic issue is energy grows. The logarithmic energy is a little bit better in the control of the free variables. It makes a completely different mathematical world if you just have a little bit more than linear growth. For your regularization for the logarithm, it can be done much easier. You just take the logarithm of 1 plus your measure. And then it's already a convex one.
Yes, if I may answer the last, I think this has already been proposed also by, for example, Bob Svensson in a similar fashion, and I think it leads to quite similar results. Yes. Yeah. If this is easier.
I like a lot your energy, but the only thing that I noticed is that if you trust this rotation dynamics simulation in that boundary value problem, they predict the most clearest strain happening variation slope, not much strength. So I don't know whether one should trust this rotation dynamics simulation. However, in that simple sheet case, you don't see a lot of strengthening. So I don't know where the truth, because some experiments on torsion of pinwise show a lot of strengthening. So I don't know. Okay, so let's go.